Excuse me, Mr. Caldera.
Good evening, everyone. Before we start the second session, do you have any questions to clarify?
Yeah, I think most of the students, they won't join today because we completed the exam by 1:30 now. So they will not be able to reach home, I guess.
All right. They can join from the mobile, right?
Yeah. Okay.
And somehow I'll share the recording, so that's fine. And this is an optional, attendance is optional for these sessions. Apart from that, any questions? Right. So then we'll start our discussion. Last session, we was completely discussed what we are supposed to do in the assessments, and today some of the things might be helpful for you to understand and do many things related to this assessment, as well as learn about this performance modeling. So let's go through a quick review about this performance modeling. So the today overview, I'm planning to discuss session 1 to session 6. These are the essential things, and you can see session 2 and 6 are very uh, near. I mean, the probabilistic distributions, among these probabilistic distributions, you might see this exponential as well as the Poisson distributions. So that's why I have highlighted those two. While I'm doing the session, I'm planning to continue session 2, and half away, once the distribution started, I'll discuss the exponential and Poisson distributions. Then I will join, I'll revert to a probability. Then I will continue to the stochastic processes as well as the queuing and queuing theory related performance analysis and related stuff. So that's a quick introduction that what we are going to do for today. Today we are learning the very first session, a quick recap as well as a quick understanding what is this performance analysis is. So performance modeling, performance analysis and stuff, performance engineering, many terms we have, more or less conceptually similar, but there are different kinds of attributes, very specific attributes we have, so we can see some differentiations. As you can see at the very beginning, if you do not properly model the performance, if you do not properly design an application, design a real world scenario, even a road, even a supermarket or anywhere, there might be huge problems, queues, even collapse under unexpected scenarios. You might see some of the loads, some of real world scenarios, unexpected number of people in a queue, which makes all these problems at the end of the day. So it's something that really complicated and really important. Both of the sides are very important to understand how these core aspects, how these core performance modeling related stuff would be work in a relevant parties. So first of all, we can go through a quick introduction to the performance analysis. Performance analysis is a systematic study. So we are going to have a systematic study of how efficiently and effectively a system, a process, or component performs its indicted functions. What you have to understand in this scenario is we are conducting a serious performance analysis for the modeling. The purpose is the modeling. First of all, we have to go for proper performance analysis. So it's a systematic study. That means we have an approach which we'll discuss in very soon, and we are learning what kind of outcomes and how we can perform to get the optimum outcome from a given scenario. We are trying to have most effective system, or it could be enhancing the processes, or it could be different kinds of obstacles in a given scenario might affect a lot for the performance. So we have to model it properly, we have to analyze it properly, we have to upgrade it, and we have to enhance at the end of the day to optimize outcome. Once it comes to the computing and engineering contexts, it's involving highly about the measuring, evaluating, and optimizing the system performance. So under this context, what we are supposed to learn is we want to see the performance measurements, how to measure a performance, what kind of measurement mechanisms, what could be the best, and what kind of evaluating methods that would be the best, and what kind of optimizing system performances are there to ensure that the objectives such as even the speed, reliability, scalability, resource utilization, and many other aspects that we have. So you would learn all these things while you are doing your activities, while you are doing these learning all these concepts, theoretical concepts, and so on and so forth. The main goal, the main objective, the target of this performance analysis is to identify where are the bottlenecks, where are the inefficiencies that we can find, and what kind of very specific limitations that degrade the system performance. So we have to identify where these performance lags are, where these inefficiencies are happening, what kind of limitations are that we are happening, and so on and so forth. So eventually this helps in guiding the designing the decisions and the capacity planning, where the capacities are, and the system improvements, large scale of system improvements we have. So we can perform different kinds of actions to get the best out from this scenario. In a computer system, performance analysis is focusing many matrices. Some of the matrices are response time, throughput, latency, utilization, scalability. All these factors are highly helpful to understand, to work on a system, and where the performances are not up to the level of that we expecting. Always we have other components like security, resource availability, technological involvements, and so on and so forth. Once we are doing these kinds of performance modeling, we have to analyze where the actual problem lies. Whether we want to optimize the responsive times, or we want to optimize throughput, or we want to have a scalable system. Many options might be there. Many options might available, as well as many options could be involved for the best performing. But sometimes we in a given system we might unable to capture all the requirements. Sometimes if the latency is optimized, sometimes the throughput might be not optimized. So there might be some features that we want to optimize, and some of the features that are essential to run. So that's the bigger piece that we have to understand. The analytical techniques, there are a lot of analytical techniques we have. Mathematical modeling we have, simulations we have, empirical measurements that we have to understand and profile the best and where the problems are and how these things are working, and so on and so forth. So what you need to understand in this subject is that we want to involve a lot of mathematics for the performance modeling, starting from probabilities distributions to capacity planning and different kinds of simulation. For an example, what if analysis. We can simulate in some of the scenarios, if this parameter change like that, what kind of outcome will be happen. If this feature is like this, what kind of output can be happen, and so on and so forth. Then we have the empirical measurements, different empirical measurements that works a lot for understand, to measure, to run, monitor different kinds of systems and the scenarios, to optimize the scenarios that we want to deal with. Now, once it comes to the performance analysis, under the special aspect that we are mainly focusing, especially the computer science, computer engineering, or it could be information technology point of view. But yes, of course, operational efficiencies and many efficiencies are there. But if we dive into the technical or the technological, the software, the computer field, we could be able to see all software, hardware, network, as well as databases could be optimized, because we want to analyze the performance before we are doing a proper modeling. Once it comes to the software systems, you might write a code. You can write something easily. But the reality is we want an optimized code, because your code is running on top of specific hardware. Sometimes if the hardware is not compatible, this hardware is not sufficient enough to support you, sometimes the program might not execute. So we want to have an optimized code which consider the time, memory consumption, and many aspects. We have different kinds of algorithms. There are thousands of algorithms implemented to make an optimized software system, which makes the performance highest performance that we can achieve. And we have a concept called data structures. Data structures also mainly focused on this optimization scenario, how to handle a given scenario in a most optimized manner. Apart from the software systems, we have hardware systems. For an example, CPU, memory, and etc. etc. All these hardware that we want to optimize. If it is a cloud environment, we have to execute thousands of millions of different kinds of scenarios. But we have a very limited CPU, very limited memory. So in case if it is a cloud environment, we could be able to dynamically change. You have to get a decision where we want to get the next CPU, where we want to increase this memory, which demand we have, where the demand is happening, in what time that we have to increase, and what time we have to decrease. Very specifically, once it comes to cloud environment, you have to deal a lot with these kinds of scenarios, because every CPU time, memory, all these things do attach to a cost, a specific cost. So the organizations want to have minimized expenses. Hence, if you optimize these cloud resources, your life is much easier and the organization might be a very profitable organization. As it comes to the networking, we have to optimize the bandwidth, packet losses. We have to minimize these kinds of scenarios and the delays of the characteristics. Where the delays are happening. Once it comes to databases, perhaps you might learn even in a separate session. Query optimization, how to write a proper SQL code or NoSQL code or whatever a code to execute, to do the best. It could be extraction, it could be input, or it could be creating a table or any other thing. Nevertheless, once it comes to the software field, computer science, information technology, almost everywhere, they are something that we kept for the performance enhancements. That's why organizations are growing day by day, which provides very smooth facilities as well as very strong outputs. So the world is really interested to see an optimized systems which is modeled the performance very well, and the performance analysis was done in a very successful manner. All these factors are giving a good starting point to think as a student who is learning this scenario, how this performance monitoring, performance enhancing can be do, and so on and so forth. So as I discussed with you, it's a scientific approach or a systematic approach that we have to solve or model specific system, any scenario, to optimize it. If I go through a very high level and a quick discussion, here we have measurements, here we have evaluations, here we have diagnosis, here we have optimizations, and so on and so forth. So what happens in this each and every stage? At the very beginning, we want to have a measurement. The measurement is collecting relevant performance data using tools and logs and so on and so forth. So we have tools, we have logs to wear and understand or get data collected to the system for the next steps. Next steps. Once we completed, we have collected thousands of millions of logs, thousands of millions of information, the raw scenarios or raw models. Then we can go for evaluation. Comparing the results against the benchmark or service level objectives. We can have a benchmark. Every customer should reach to a given system like within this much of time. Or in a given scenario, this kind of a queue can maintain only 3 people at a given time. Many other aspects are there. So we have to compare results against this benchmark. You can tell 3 people in a queue, or the system should load within 2 seconds. Or you can state the system should receive this network in a given nanosecond, or system should shut down within this kind of milliseconds. It's benchmarking. All the examples that I have given is a measurable value that we have. All these measurable values very specifically mentioned, and what is the benchmark is 3 people in a queue. 3 is the benchmark. If it is exceeds or not, then after we can do whatever the analysis that we have. That's why we have benchmarking. We initially assume, or we kept a specific value to tell this is the best or the most effective and most efficient method. So benchmarking that, we do the calculations. Then it's relatively do the calculations. Or else it could be a service level objectives that organization has defined. Organization needs to have this kind of a specific service support, service level agreements we have, service level objectives we have, or any other factor related to the evaluation. After the evaluation, we can identify the cause of poor performance or the inefficiency is. Where are the actual process lags, or the production line is something that taken like a lot of time. Supply chain management, even in a given a very simple supermarket, why the people are in a long queue, even an ATM machine, in front of an ATM machine. Some of the time you could be able to see huge queue in a specific date and time, and the same ATM you could be able to say no person at all, it's completely empty. So if you are the manager, if you are the IT head, how many ATM machines that you want to do implement in this place, it depends on the identification of the diagnosis. We have to identify where the poor performance is, because if there's a place that ATM machines are required, like for an example we want 3 ATM machines in a given place, but you have seen a huge queue on a specific date and time, which is peak. At that time, you do the calculations for 10 ATM machines, then you recommend it for 10 ATM machines. then your manager might get upset because afterwards your manager might realize actually there's no required for 10 ATM machines. The reason behind it, it's only a very specific scenario in a very specific date and time that's happening, not in every day. But there is an optimal number of ATMs, optimal number of queues. All these things depends on many factors. That's why we are doing this kind of a diagnostic. After the diagnostic, we can go for the optimization. We can apply different kinds of enhancements and we can see what kind of optimizations would be the best for a given scenario. That's a big question that you have to deal. That's the biggest question that we want to involve in this subject matter. It could be capacity planning, it could be queues, it could be any other factor. We want to see what kind of optimized scenarios that we have. By the systematic analysis of this performance, engineers and analysts can ensure that systems meet expected service levels, remain cost effective, and provide high quality user experience. So eventually what we want to do is we want to give the optimal things. Sometimes there might be a couple of people in a queue, because if we take unlimited things, then that's not the optimized, because we want to deal some for other scenarios also. That's the big picture that you have to think in your point of view. Shall we go for a quick activity? It's in your LMS. I'll give 2 minutes for this activity. It's in LMS and session one. Under the session one, you can see there is a question, a very easy question to do this interactiveness. So once you start, it's waiting only 2 minutes. After that, it will be automatically submitted. So whatever you learn, you can answer for this kind of a simple question. We'll go to the next session after 2 minutes. Quickly start this activity and complete it. Right. So I believe most of you have completed this activity. So let's move to the next session, overview of probability in performance modeling. Now, performance modeling has very specific requirement for the distributions because probabilities. So that's the core and the fundamental concepts. So perhaps you have learned these probabilities and other related stuff uh, during your degree period, but I will go through a couple of quick things that essentially that you have to understand. Probability forms the mathematical foundation for performance modeling. That's the initial factor because performance is always something based on probability. If it is complete failure, then yes, of course, there's no probability system is failed, no more optimization is required. Apart from that, all the things we have some probabilistic output. So that's why we specifically telling performance modeling is very important because that's the fundamental scenario where system behavior is analyzed under uncertainty. So we have to analyze the systems under uncertainty. We have uncertainty every time. The real world systems like computer networks, web servers, databases, all these things, right, inherently non-deterministic meaning of these response times, service rates, rivals of requests, very unpredictability. Probability theory allows us to variations to be represented and analyzed systematically. So that's the key point that we have to understand. The probability theory is allows us to, it's giving a chance for you to understand and how to analyze, how to model a given scenario properly. So that's the big picture that we have to keep in mind. Probability allows analysis to predict expected performance metric. Now, what we are supposed to do at the end of the day is we have a specific performance metric which is specifically telling how it's working, assess the risk, and optimize the resource allocation. Even when extract outcomes are unpredictable, thus probability is not just a mathematical tool. That's the backbone for all of our stochastic and KV models in performance evaluation. So we have a very detailed and very important factors in this probabilities distribution and predicting all these things. But every prediction is something in a percentage, not zero, not one, in between 0 point some value. The reason behind is if it is one, that means fully completed, and we are pretty sure it could be happen. There's no nothing guaranteed it's happening. Zero means it never happens. Guaranteed, there's no possibility to have happen that kind of a thing. Probabilities in between that, and what we are doing also, we are doing this performance modeling and optimization analysis and all of these things which is highly based on the probability, because if you learn very soon all these things, Kivy theory and stochastic processes, all these things, we have some assumptions. Based on these assumptions that we are doing, all these things are based on the probability. So what happens at the end of the day, we are learning in detail all these aspects one by one. So that's the biggest opportunity for us, because we are telling some of the percentage up to some extent. It's based on the probability. We can't give a guarantee in anywhere it could be 100 percentage, because we are based on specific probabilistic mathematics. So if it is a probability, that could be vary, but based on the data we are trying to have the optimal scenario. We are trying to have the best scenario that fit for the given situation. Role of probability, this performance modeling. So here we have the most interesting part. Performance modeling uses probability to describe random events and quantify uncertainty. Now we have uncertainty that deals, and what we are trying to do is we are trying to have this uncertainty to quantify in a system operations, very specific system operations that we want to deal with this kind of a scenario. Instead, for extraction of these predictions, models use probabilistic measures to express how likely certain outcomes. For example, delays, failures, or sometimes query length. So we want to see how the system would work as expected in the performance metrics. Average response time, throughput, probability of delay of the system overloads, reliability and availability of the components, and etc. etc. So the probability is the backbone, as I discussed earlier, the performance modeling. Based on that, there are thousands of paths created, and it's moving to very complicated and very essential modeling mechanisms in nowadays. So we have a very important concept, random variables and the distributions. Under the performance models, we have random variables, something random, that used to represent the system quantities that vary with the time. So that vary with the time, we have very specific components, anything that fit for the scenario. We have named three concepts: arrival time, service time, as well as inter-arrival time. Arrival time is specifically telling, which is lambda, number of requests arriving per unit time. It could be a minute, it could be a second, it could be an hour, it could be a day. Arrival time. Number of requests, it could be number of people in a queue in a given hour or a given minute or a given day, or any slot, any time unit. Then we have a service time, which represents the time taken by whatever the server could be a machinery server, or could be a counter, cashier, anyone, to process the request. To process a specific request, it requires a bit of effort. Inter-arrival time is time between consecutive arrivals, first one and the second one. So based on this inter-arrival times, we have lot more logics developed. For an example, random arrival inter-arrival times, or the specific or equal time slots time between each and every component, and so on and so forth. So the random variables and the distributions are very important for these aspects, where we have to deal in different kinds of different factors that dealing in many aspects. These random variables follow probability distribution that describes their statistical behavior. How this statistically it's distributed? So we have mainly three components. It is very common: exponential distribution, Poisson distribution, as well as the normal distribution. Now, exponential distribution is specifying models with memoryless process like Poisson arrivals or the service times. In the other hand, we have Poisson distribution, which describes the number of arrivals in a fixed time interval. So Poisson distribution keeps an assumption, or it's describing the number of arrivals in a specific queue is in a fixed time interval. In between the time is a fixed time. Normal distribution is specifying, approximates, integrated, or average the performance metrics, find the optimal scenario. Yes, of course, based on the scenario that throws to you, you have to select most optimal distribution. And once it comes to real world data, you have to see whether it's an exponential distribution or a Poisson distribution or it's a normal distribution. Based on that, the way the calculations and many things might be different. Before we proceed further, any questions that you need to clarify? All right, next, see uh, the session 6 as I initially informed you, so we can discuss some of the things very specifically related to the session 6, which is exponential and the Poisson distributions. Then we'll back to our discussion. So let's have a quick discussion on this exponential and the Poisson distributions under the performance modeling point of view. The exponential and Poisson distributions are two fundamental probability models widely used in performance analysis and queuing theory. Before I dive, could you please raise your hand if you have done exponential and Poisson distribution before this session, or if you know already what is this Poisson distribution is, what is this exponential distribution is. Could you please raise your hand to check your existing, you want to get some understanding. All right, seems no one learned before these distributions. They describe random, memoryless events such as task arrivals, packet transmissions, and service completions in computing and communication systems. So we have to understand the randomness, the memoryless events. These are two essential components. For an example, we have task arrivals, packet transmissions, and so on and so forth. All these things, all these things could be under the category of random and memoryless events. So what is this random as well as memoryless? Random is not a big deal. Random means it's just a sudden situation, perhaps without any specific distribution, it suddenly happens. So we assume at the very beginning it's a random scenario. Then we have memoryless events. What is this memoryless events means? It's not considering the previous scenario, right? So how these things could work and so on and so forth. That's something that really important to understand. Now we'll get this example. Now assume that you are in a taxi arrival. Assume there's no mobile application or any other thing. You just went outside and you are waiting for a taxi. There's no memory. Why there's no memory? Because there's no consideration of your arrival time. For an example, you came to the road at 7 a.m. The taxi has no idea at what time you came to the queue or the specific place. Sometimes you might get a taxi within minute, or sometimes it might be 2 minutes, or 3 to 5 to 10 to, or even half an hour, or forever you can't get it in that day, because it's a memoryless situation. They have the scenario has no idea what action happens at the very beginning. But if you are going for a buses run in a proper schedule, so it's not memoryless. It's a scheduled, it is a uniform mechanism. So for sure, if you go for the queue, if all buses are starts work, their day-to-day life, they work. If you went, like if it is the uh, buses are like every 5 minutes or every 10 minutes you'll get a bus. So if you go to the queue or the place that you are sitting, wherever the place, specific place, then that time too, there might be maximum 10 minutes, because within every 10 minutes we'll get a definitely a bus. So we have an argument constructed in here, because it's not a random distribution all that. In Sri Lanka it could be much assumptions, because we have this personal experience. Even though it's scheduled, for sure there might be some delays. It's a different scenario, but assume that all these things, all the bus drivers are very good and they drive in a proper time and all these things. They are very honest, especially private bus owners are very honest, right? So we'll assume all this honesty, and we'll see how these things happen. So it's based on the not memoryless scenario. If you go back again, these exponential Poisson distributions are task arrivals, packet transmissions, or any other thing in computer and computer. I believe you understood what happens in this scenario. Let's dive to the next factors. These distributions, that means Poisson and exponential distributions, form the backbone of the Markovian models. We have a couple of models. We'll discuss all these cues today in a quicker and a rapid manner. That are used to derive analytical performance matrices such as utilization, response time, and queue length. So we'll discuss this MM1, MMC, and MM infinity and all these things queues very soon. Then you'll get understanding a bit more. The Poisson and exponential distributions are essential building blocks in performance modeling. So it's a very important. They able to formulation of Markov models, simplifying analysis through memoryless properties, and help predict critical performance measurements such as waiting times, queue lengths, utilizations, etc. etc. Here we have a mathematical framework to capture randomness, uncertainty, and time behavior in computing and communication systems. So this is a very important factor. It's a very important factor that deals in this kind of a scenario to get something work done. Let's have a quick discussion for the Poisson distribution. The Poisson distribution, which is modeling the arrival, is based on a specific equation. Poisson distribution models the number of events. We have specific event. Event could be in a queue, in a data packet, or any other scenario that occurred in a fixed time intervals. Every 5 seconds, every 5 minutes, every 5 hours, 2 hours, 1 day, 2 days, 5 days, or whatever fixed time interval when the event happens, independently of each other. So the first person to second person, first bus to second bus, there's no connection at all. Those are independently executing, and consistent average rate. The average rate is consistent where this whatever time these distributions are coming. So if we can easily do a mathematical modeling for this, nt represents the number of arrivals in a time t. So we have a quick equation where nt equals to k equals to lambda k and so on. So I don't think so. You want to learn about how these things was proved, how those things was proved. So you don't want to bother for that. You just go through the equation and keep in mind you have to memorize this equation to do the math calculations. If it comes to the real world scenario, sometimes you might assume that we want to memorize, why we should memorize all of these things, because for the examination you have to use it. We have lambda, which is average arrival rate, events per time unit. Then we have k, number of arrivals in time k. That's how the distributions are happening. That's how the distributions are working for the best scenario. Here we have some of characteristics, how to calculate the mean, variance, and the additivity, the sum of independent Poisson processes. Is also so. Let's have a quick discussion on this exponential distribution. Exponential distribution, modeling service, and inter-arrival times. If you go back, here we have modeling arrival processes, which is the Poisson distribution. Here we have modeling service and inter-arrival times. So you can see one additional factor is considered in here. The exponential distribution models the time between successive events in Poisson process. The exponential distribution models the time between successive events. It defined by a rate parameter which is lambda. You could be able to see the lambda representing the expected number of events per time. We want to see the expected number of events specifically per unit. The probability density function is mentioned as ft lambdas is valid, where the t is greater than 0. That's a very important factor. And once it comes to CDF, which is cumulative distribution function, then the function can be executed like this. We have a couple of properties where mean, the expected value, the variance, as well as the memoryless property given in here, which is means to success. This means the future probability of an event is independent of how much time has already elapsed. I'll share a couple of questions with you, so you could be able to go through and understand some of mathematical questions. Yeah, of course, for the examinations you need, but I don't think so in real scenarios like programmatical point of view. There's a huge requirement. What are the limitations that we have? While the Poisson and exponential models are mathematically convenient, what happens? It's assuming memorylessness as well as the constant rates. Real workloads often exhibit closeness, correlation, or it's a heavy laid behavior. So whenever you're doing some advanced distributions like Pareto, then for sure you want to ignore all these things that you have learned, and then you need to work on a specific scenario. Still, these are two distributions remain fundamental for the analytical work. So the fundamental analytical work that we are working on this approximating of this modeling and so on and so forth. I have gone through a very quick discussion with you for the Poisson and exponential distributions, but I would strongly argue you to solve some of mathematical questions. You can go to any book. There are a lot of books related to this Poisson as well as the exponential distributions. So please make sure to go through all these things, do some math calculations, and think and see where the things would work. So it is very important at the end of the day. And we'll back to the probability, the standard probability that we want to learn. Here we have the events and the state transitions. In the stochastical models like Markov chain, so the probability is used to describe transitions between system states. It could be different kinds of states in the real world scenario. Like for an example, a person in a queue and in the counter and leaving. So there are three states that we are speaking in here. That's a transition in between the system states. So these whatever the items, whatever the person, network packets, digitally or manually or whatever the way that we have to deal with these kinds of things. For an example, the probability that a queue moves from 2 jobs to 3 jobs in the next second. Such models are crucial for analyzing steady state probabilities. So this could be help predict long-term performances on the generated characteristics and stuff. So this is a very important factor where the events as well as the state transitions that goes towards. Then we have conditional and joint probabilities. Systems often exhibit dependencies between variables. For an example, the probability that a request is delayed may depend on the number of users in the system. The probability that a request is delayed may depend on number of users in the system. Conditional probabilities, such as we can see queue length is greater than 5. This help model such relationships. Then we have joint probabilities. For an example, P is are also used when analyzing correlated systems. It's related components. So the correlations and the correlation mappings could be able to taken out. So I would see all these things in a probability point of view, which is very important, and that's the real requirement, and that's the real story that we have to deal in this kind of a scenario. And couple of applications in the performance analysis as well as the performance modeling, giving models, reliable models, workload characterization, capacity planning. Probability determines waiting times and system utilization. And the system utilization is required. Then the reliability models. What kind of reliability models we have? Probability estimate system, failure and repair time. Workload characterization, randomness in arrival and service processes. So we have capacity planning. I will do a complete separate session for the capacity planning. This is very important to understand how the capacity should be measured, how the capacity should manage, and so on and so forth. So there are a lot of factors that involves in these kinds of things. So I would strongly argue and strongly believe that you should understand and run these kinds of things in detail. So please think about these applications, then for sure you can go through the best. Up to now, any questions? We have completed session 1 and session 6 in a very quick and fast and rapid manner. Any questions? All right, let's move to the next scenario. We have stochastic processes. Stochastic processes. What are these stochastic processes? And what happens in stochastic modeling? This is very important. A stochastic process is a mathematical framework. It's basically a mathematical framework. This is used to model systems. It's used to model systems that evolve over a time in a probabilistic manner. In a probabilistic manner, it's evolved over the time. It's changing in a probabilistic manner. So it's changing, right? These models are changing over the time, but in a probabilistic manner. In performance modeling, stochastic processes help describe and analyze. So what happens in here? Stochastic processes are help to describe and analyze the random behavior of systems such as servers, communication networks, and distributed computing environments. Since the system's events like task arrivals, service completion, or component failures occurred, unpredictability, deterministic failures to fail to capture their true dynamics. What happens in here? The system events like task arrivals, task can be anything. It could be a customer who is arriving to the system. Service completions, completing a bill or any other thing, or component failures, anything. System is not working at all. Occur unpredictability. So this could be happen unpredictable manner. Deterministic models fail to capture their true dynamics. So the deterministics would not support you for this kind of a scenario. Stochastic processes providing a probabilistic approach to understanding and predicting system performance over the time, because it solves the unpredictability in deterministic models, because uh, components failure cause unpredictability and so on and so forth. Stochastic processes provide the mathematical backbone. So this is providing a mathematical backbone for the performance modeling. Now we have two components we have discussed. One is the probability, second one is mathematics. For the mathematical backbone, we have to go through stochastic processes. Now you should understand there are three main concepts that focused today. One is probability. The two concepts, one is probability, the other one is mathematics. Under the probability, we have mainly two components, Poisson and exponential distributions. Once it comes to the mathematical backbone, we have to speak about the stochastic processes. They enable analysis to handle uncertainty, capture dynamic system behavior, and predict long-term performance characteristics. So we have to understand these processes for building, analyzing network, reliability models, simulation-based performance studies, and many other XYZ facts. This is very important and which is very powerful to deal and get our work done. So what you're supposed to do is, what you need to understand in this kind of a scenario is, we have to deal a very important, a very detailed factor in this kind of aspect. So the definition for the stochastic process is a collection of random variables. Here we have t, which is representing the rest, representing the time, whether it's discrete or the continuous, that's fine. And xt represents the system state. That's why we have discussed if we have different kinds of states in a given system to understand how it's evolved this time t. The processes describes how the state of the system changed with the time according to the certain probabilities. We have very specific probabilities. For an example, in a given system, xt might be represent the number of customers in the system at time t in a given snapshot. In a network, xt might be denote the number of active connections at a given instant. So what we have to understand is, in a given scenario, how these facts are represented. We have mainly two types of stochastic processes. One is discrete time stochastic process. The other one is continuous time stochastic process. Let's go through quickly what is this discrete stochastic process and the continuous time stochastic process means. Discrete time stochastic process, the time evolves in discrete steps. For an example, t equals to 1, 2, 3, 4, which is a very specific time, a snapshot where time t equals to 1, time t equals to 2, time t equals 3, and so on and so forth. That's why discrete time stochastic processes are. It's used to systems where the events at fixed intervals. For an example, packet transmissions around time slotted scheduling and many things. We have a unique specific time that we have plotted. The other one is continuous time stochastic processes. What happens in time is greater than or equals to 0. That means anytime. So it's a continuous time, common in real world systems like server queue requests or the component features or any other thing, where the events can happen at any instance. That's why we have to deal with this continuous as well as the discrete time stochastic processes. So that's the two types in this context. Now, stochastic processes, once it comes to the modeling, the performance modeling, we have Poisson processes, we have Markov processes, we have birth-death processes. So all these factors are really essential to understand how these processes are working. If we go for the Poisson processes, we have the models, random arrivals over the time. So for an example, customer requests or the network packets. So we have no control over these things. So it's a random arrivals in time. So it's defined by the rate parameter where the lambda is equals to the average number of arrivals per time unit. So it's average time of arrivals per time unit. Then we have key properties. What kind of key properties we have? Inter-arrival times are exponentially distributed. Right? So we have inter-arrival times that are exponentially distributed. The process is specifically memoryless. We are getting memoryless, meaning past events do not influence for the future things. So it's a very important property in the Poisson process, right? So inter-arrivals are exponentially distributed. The process is memoryless. That means we don't want to keep anything. No influence for the future facts. This is widely used in queuing theory and traffic modeling. So it's very important and valuable fact. Markov processes. What kind of Markov processes we have? Describes the systems where the future state depends only on the current state, not the past history. So it's describing the systems where the future state is basically depending only on the current state. It is not on the past history. And this is characterized by the transition probabilities between states that we have to deal with. The Markov property makes analysis mathematically traceable, enabling the derivation of steady state performance metrics like system utilization and delay. So the Markov process is a very interesting and really valuable story. So it's described the systems where the future states depends only on the current state. So that's the factor. If you go back, you can see here we have process is memoryless, meaning past events do not influence future arrivals. That's the Poisson process. Here we have Markov process. Markov process is telling future states depends only on the current state. Where your object or whatever the things in the current state, based on that, we are telling the future things, not the past history. Characterized by the transition probabilities in between these states. After this transition, it could be a new object or a new scenario, whatever state, then it happens, then it moves to the next state and so on and so forth. The Markov property makes analysis mathematically traceable, enabling derivation of steady state performance metrics like system utilizations and delays and so on and so forth. The third process is birth-death process. It's a special type of Markov process used to modeling the queuing dynamics, so the queue dynamics. It's a special type of Markov process. Now, previously we understood what is this Markov process is. This is a very specific scenario, a special type of a Markov process that modeling the queue dynamics where the dynamicity is represented. Birth, the birth word, birth representing arrivals of new jobs or specific packets, and the death representing where the service is completed. So we have MM1, MMC, KV models that commonly use this birth-death processes and so on. I believe it's so interesting. Any questions? Sadhun, Sampath, any questions? I'm just random asking from students. Any other one? Any other questions that you have? All right, let's move. The application in performance modeling. Stochastic processes from the foundation of quantitative system performance evaluation. So we have QV models, reliability modeling, network traffic modeling, resource allocation models, and so on and so forth. Here we have stochastic processes from the foundation of this quantitative system performance evaluations. So we have to understand very specifically how the QV models can be used to predict average waiting time, queue length, and system utilization. The reliability modeling to analyze failure and repair patterns of system components. We have network model traffic modeling, which is used to represent random packet arrivals and connection durations. We have resource allocation models, which is used to forecast workloads and optimize scheduling under uncertainty. For an example, a web server model, arrivals of requests can be represented by a Poisson process and service mechanism by exponential distribution and so on. Together we have a membered queue, which is allowing analysis to compute key metrics such as average waiting time or probability of delay. So that's the big story that you have to keep in mind, how these performance are modeling. So we have QV models, reliability models, network traffic modeling, resource allocation models, and so on and so forth. Performance metrics derived from stochastic modeling. So we have a couple of things. Using stochastic processors, we can derive steady state probabilities, long-term probability that system is in state I, the mean queue length where L, expected number of jobs in the system, mean waiting time W, expected delay experienced by a job, system utilization rho, we have fraction of system is busy. So that's, we can derive the stochastic process, we can derive based on these factors. These metrics provide a quantitative for evaluating and optimizing system performance. So that's all for the session 3. Any questions? Sorry, yeah, session 3. Session 2, right? Session 3. Any questions? Right, let's move to the session 4, fundamentals of queuing theory in performance modeling. Queuing theory is the mathematical study of systems that provide service to randomly arriving customers or tasks. In performance modeling, queuing theory is one of the most powerful tools used to analyze and predict system performance under varying workloads. This enables us to evaluate how system resources, servers, processors, network links, etc., handle demand and where the bottlenecks occur. So we have a mathematical study of the systems provide a service to randomly arriving customers or tasks. Queuing theory is a mathematical study of systems that provide service to randomly arriving customers. So we have no idea how these people are coming. It's a random arrival and arrival customers or specific task. It could be a network or any other thing. In performance modeling, queuing theory is one of the most powerful tools used to analyze and predict system performance under varying workloads. We have different kinds of workloads, so we have to understand how it's working. It enables us to evaluate how a system resources. It's enabling and it's giving a power to evaluate how the system resources such as servers, processors, network links, etc., working. Handling demand and where the bottlenecks occurring. So the QE models are used in computer systems, data centers, communication networks, and manufacturing systems to estimate waiting times, resource utilization, and throughput. So the QE models are used to many other places like computer systems. We have data centers, large data centers. We have communication networks, internet, the biggest communication network, and manufacturing systems. There are a lot of manufacturing systems that we deal to estimate waiting time, resource utilization, as well as throughput. So it's a very important. These are very important to understand how this queen theories work. Before we dive into the details, we have to initially understand a very important law, which is the Little's law. Anyone can explain, can someone can explain what is Little's law? In a simple scenario, just go to the web and see how the Little's law started. I will give 2 minutes. I believe everyone going through Little's law and how it works. It's very interesting. Little's law is one of the most fundamental principles in queuing theory and performance analysis. It provides a simple but powerful relationship between three key quantities in stable queuing system. We have three factors L equals to lambda W, and we have a derivation of the same equation. L is average number of customers, could be jobs, tasks, packets, etc. in a system. Lambda means average arrival rate, number of customers arriving per unit time. W means average time a customer spends in the system. It could be waiting time plus the service time. Little's law holds for a stable queuing system regardless of the arrival or the service processes. So very important law is given for us. So this is a quick explanation for you. What is this Little's law? It states that the long-term average number of customers in a stable system L is equal to a long-term average effective rate lambda multiplied by the average time a customer spends in the system. So this relationship is specifically holding for any stable system regardless of some of the factors like the arrival processes that we have considered as deterministic, Poisson, etc., where the system, the service time of this distribution, we don't want to bother for that. The number of servers that we have, the service discipline, whether it's first in, first come, last in, first out, or priority base, etc. So that's very important. That's why we have to deal with this kind of a scenario a lot. Let's now apply for many things: performance modeling, manufacturing systems, service systems, project managements. So many aspects we have that we can deal with the Little's law. And there are a couple of variants that we can find in the Little's law, depending on where the measurements are taken. If we have taken for the entire system, we can consider the specific equation, or if you want to get for a specific Q, then we can get the same equation by a specific average number of waiting time in the queue as well as average waiting time before the service begins. So that's what we can have a derivation. This is a quick derivation of the same instance. Let's dive to that's a quick information that given to you for the caving systems. Regardless of many factors, Little's law works up to good extent, but we have some more additional things to understand. So let's have a quick discussion on these kinds of things. What is the basic structure of the queuing system? A queuing system consists of three main components. We have three components: component 1, 2, and 3. Here we have the arrival process, service mechanism, then we have queue dispatch. The arrival process is describing how the jobs or the requests arrival at the system. How these things are coming to the system. Arrival process. Often modeled as Poisson distribution, Poisson process with inter-arrival times that are exponentially distributed. Then the average arrival rate is denoted by lambda, which is representing the number of arrivals per unit time, per specific unit time. We have service mechanisms defining how the requests are served once they reach the server. Then we have the service rate that is denoted by mu, representing the average number of jobs completed per unit time in a given specific time. Service times may also follow an exponential distribution in many practical modes. We have many practical modes that we are dealing with. We have queue discipline, which determines the order in which requests are served. So we have a couple of policies: first in, first come, shortest job first, priority queues, and so on and so forth. So the structure of the queuing system is very important. We have to understand how the queue discipline works, how the service mechanism works, as well as the arrival process. Based on that, the queuing system, the usage of the queuing system, internal mechanisms, and many other factors might impact a lot. To represent the queue, we have a notation known as Kendall's notation. Under the Kendall's notation, queuing systems classified A, B, C, K, and D kind of a representation we have. So we have A, arrival distributions, B, service time distributions, C, number of servers. These are mandatory. Now you can see some of essentials given in here. This ABC represented in here, MM1, MMC, MG1. So this is MM1, MMC, MMG. Likewise, we have essentials. These three components are essential. But the K and D is not essential, it's an optional. Maximum number of customers in the system, so we do have no idea. In case if you have the maximum number of customers in the system, you can add it. The population size, if you have such details, you can add the population details. If you have the service discipline, so we can add D in here. So these are the common explanations or the common examples. We have M1. M means M for Marconi confidence, which is Poisson. So we have a single server, Poisson arrivals, exponential service times. Multiple servers, Poisson arrivals, and exponential service times. Here we have single server, Poisson arrivals, general service distributions, and so on and so forth. So this is very important how these factors would work, because this is the scientific notation, the scientific method that we are writing, MM1, MM0, MMC, MG1, and so on and so forth. So you could be able to see all these things in whenever you are referring any kind of a book. Here we have queuing theory provides key performance indicators that describe the system's behavior. Here we have lambda, which is arrival rate, mu, which is service rate, rho, the utilization, and we have LLQ, WWQ. Here we have the average number of arrivals per time unit. Here we have average number of arrivals per time unit, average number of services completed per time unit. Then we have fraction of time the server is busy, where rho equals to lambda by mu. Average number of customers in the system, where the queue plus service. Average number of customers waiting in the queue, as well as average time a customer spends in a system, then the average waiting time in a queue. So we have a lot of facts that dealing in this kind of a scenario, where the essentials of the queuing theory and other related stuff would work. Again, there are a couple of common queues. We have MM1, MMC, MG1, MM infinity. So very interesting queues. We have the other variations we have. Let's dive a quick overview to understand very basics of these things. MM1 cube is the simplest version, which is the most simplest version, and it's most used the analytical model for the performance analysis in our cases. This is basically representing a single server system. So we have a one server, the activities are conducted. And we assume that we want to see arrivals follow the Marconium or these Poisson processes. Service time is Marconium, which is exponentially distributed, and we have one server. So that's the arrival follows service times as well as the servers. You can see, which is the same notation that you can see. If you can remember. Sometimes if it's day one, it could be a bit complicated here. ABC is a factor number of servers, right? This is ABC M1, right? M1. M comes from here, M comes from here. Number of servers is 1, right? So that's what we have defined here, this MM1Q. Right? MM1Q. This is the stored MM1Q, which is a single server system. We have one server, and the arrivals and the services times are also following the Markovian distributions. And we have MM1 notation comes from the Kenda's notation where ACS and stuff is going on. So that's what we have to understand in this kind of a scenario. Then we have A is arrival process, and we have S service time distribution. Then we have number of servers. A happens in here. So we have MM1 where the Poisson arrivals, Poisson services, and the single server is working. Right? Any questions that do you have? Any questions?
So, excuse me. Hello.
Yeah. Please go ahead.
Sir, how this Kindle notation are related to little law?
Little slow is a different story.
Uh,
That's
uh,
why I have taken it in a separate forum, unless you might get confused, right?
uh,
So it's a separate story. Don't go for that in this case,
uh,
right? So this is something that's a different story that I'm speaking. That's why I started at the very beginning. It's working for many XYZ facts.
mm, mm. Right, sir.
Right. So I believe you understood the core concepts. Right. We'll go to the assumptions in this MF1 model. So it's built on the following assumptions. We have arrivals following a Poisson process with a rate of lambda, the average number of arrivals per the time unit. Then we have the service times. Then we have one server. So these are the assumptions that we have in the system. The system has infinite queue capacity and first in first out uh, discipline is focus. The system state the number of customers evolves as continuous time Markov chain. So I think you can remember we have discussed two factors in the time factor. We have continuous as well as the discrete. So this is focused on the continuous time Markov chain. Here we have MMCQ. This generalizes the MM1 model to C parallel servers. So we have C number of servers. It could be any like 5, 14, no, whatever things. It's providing services at the same rate, which is widely used in performance modeling for systems. There are multiple servers like CPUs, web servers, service agents, and income requests simultaneously. In, if we have the connotation, we have the Poisson arrival, then the exponential distribution service times, and the number of services given here. Then we have the applications, multi-core CPUs or the threads in a processor. So we have web server farms, so the cloud instances, call centers with multiple agents, network switches with parallel processing units, and many other factors we have to deal with. Here also we have couple of assumptions. It's around arrival follows Poisson process with a specific rate of lambda. Then we have the service times, which is exponentially distributed with a specific rate of mu. That's the value that we are taking. C is identical servers. So keep in mind, these are identical servers. If these are servers are different, then there is a huge problem. Yeah, identical servers, request in the parallel. And we have the queue in FIFO, first in, first out, and infinite queue capacity, which is no liquid process and stuff. The system is stable. Lambda is lesser than C into mu, which is the total service capacity exceeding the arrival rate. Then we have another queue. These are different kinds of queue representations. Here we have MG1 queue. Here MG1 queue is an extension of MM1 queue. So we have again Marconi process. Here we have the general service time. Here we have one single server. So the difference is G is an extension of this M because it's a generalization of the general service time distribution. It's an arbitrary, not necessary to be exponential. If the service time is exponential, then we are taking MM1. Here, if it is arbitrary, so it's not exponential, so we can go for MG1. MG1 model is allowing to have more realistic services than MM1 while still keeping the analytical traceability using PK formulas. So you can learn all of these things whenever you are free, how these PK formulas and stuff is spread. Systems where service times are available or non-exponential, such as disk access times, batch processing tasks, networks with stuff. So it's very common kind of a thing that we can go through. Again, we have the assumptions are going through. I'll quickly go through this kind of scenarios. Here we have infinite queue, which is the infinite server model. So here we have theoretical model used to performance analysis to represent unlimited number of servers. We have infinite number of servers, which is not practical scenario, but assume we have only 300 customers in a given business and we have 301 customer support executives we have hired. Then in such cases we can consider it as an infinite, because for sure all the customers, 300 customers, we have 301 customer service representatives we have. So one-to-one mapping was done. Still we have one remaining, which is something that we can consider in a theoretical manner. Unlimited number of servers we have. Again, we assume it's Poisson arrivals. Here we have exponential distributed service times. Then we have the infinite time. If it is MG infinite, which is the generalized version. Now you can use the kernel methods and you can do required updates in this kind of a scenario. Again, a quick set of assumptions that we have. Arrivals follows the Poisson process with the rate of lambda, and we have the service rates and the exponential distributed with the rate mu and infinite number of servers. So there's no waiting occurs, zero waiting at all, because whatever the time the customer is arrived, the customer is served immediately because we have infinite number of servers. Queue discipline is irrelevant since there's no queue at all. The system is stable for any lambda, any given lambda, all lambda, because capacity is unlimited. So this is the most optimal case if we can go through, but for sure organizations do not allow for this scenario. Couple of applications that we can go through the modeling systems where the requests are never queued because each intermediate service. For example, here we have large-scale cloud services with elastic resources, massive parallel computing, call centers with virtually unlimited number of agents. We can have virtual unlimited number of agents, right? Because if it is a chatbot, we can have unlimited number of agents. Not a real world example, like a 100% accurate example, but just think a ChatGPT that you are using. It's an agent that calls for all these models and get the responses. We have to assume that's unlimited number of agents that we have, unless a very specific case, even the entire world logged in, it's working more or less in a very smooth and successful manner. So we have virtual unlimited number of agents that gives the responses for you. Although it's idealized model, TFMM Infinite provides insight into the system utilization, concurrency, and resource requirements in high capacity environments. So this is very important to get to deal and get something done. Let's dive to the session 5, which is the last session. I believe I have gone through in a bit of faster phase. But yes, of course, you can go through all these things. I will upload this link as well as the what we call this PowerPoint for you. I got to know that the Zoom links are set to expire. It's automatically the Zoom links are expired, so I don't want to mess up the life. So I don't share the Zoom links. Instead of that, I'll use the standard method that I'll upload to somewhere else and I can share the link unless in the latter part I have to do again another recording for you. Right, so I'm not sharing the Zoom link today for this one, but I'll upload to YouTube or somewhere else too. You can download it, you can do whatever, you can share these videos, so I don't bother. You can download, it's up to you, and you can use it for your work. Here we have the application of Kevin theory for the performance analysis. Here we have the Kevin theory provides a quantitative framework for evaluating how systems behave under a load, and its applications in performance analysis to help determine whether system resources such as servers, CPUs, networks, etc., etc. By applying QE models, performance modeling analysis can predict diagnostic and all these things that we can do. Yes, of course. Right. So you learn all these factors now. The purpose of the theory, this is very important. This slide is extremely important. The key purpose of using QE theory in performance modeling. Some of examples given for you. Actually, this slide I have created to make your life much easier. Predicting system performance, capacity planning, bottleneck identification, resource optimization. All these four, what I believe is you can use for your mini project. Right? You can get any problem among these things. You can predict the system performance, or else you can consider how to do a proper capacity planning, how to perform a proper bottleneck identification, how to conduct a proper resource optimization and stuff. And this is your case study. What if analysis? Your case study. This is your case study. What if analysis? Testing how performance changes when parameters are changed. Right? When the parameters are changed, how the system behaves. So this is basically your case study, and you can take any of these factors. Even you can take the last one, right? So these factors, what I believe is that's the best for your mini project. You can think whether we want to go for estimating the average delay throughput, and utilizing under different kinds of workloads, determining the required number of servers or the resources to achieve target service levels and stuff. Then the bottleneck identification, locating the components that cause conditions or specific service delays. Then balancing workload distributions across resources to improve efficiency. So you can think what I suggest is, but it's not limited. You can think anything. This is the best mini project topics that you can consider. Here you have what if analysis. Then this is what you have to do in your case study. So that's the big picture that I want to give for this purpose of this given theory and the performance analysis. Not only that, you can go for many aspects. Then these are some of additional help that given for you to get your work life easy. Right. Next, mapping the real systems to the QE models. Now, we understood many QE models we have, so we can map into real world scenarios. In a practical performance modeling, in a live scenario, real world systems are abstracted as QE models by identifying. So we can abstract these things by customers, servers, arrival rate, service rate, many facts. Customers. So you can, for an example, user requests, different kinds of transactions, different kinds of packets, right? So we can have servers, the resource processing workload, for an example, CPUs, databases, network links, and so on and so forth. We can have a rival rate, the lambda, which requests the entire system service rate, mu, the rate which servers complete request. So we can have scheduling policies, so it's based on whatever the way that you are dealing. Once these parameters are known or estimated, appropriate models, for an example, MM1, MMC, MMG1, can be selected to represent the system behavior. Then we have applying this queuing theory to performance analysis is extremely powerful, theory driven, as well as to understand improving system efficiency. And this bridges the mathematical modeling as well as the practical performance management by predicting response time, utilization, throughput based, and stochastic behavior. So some of the things that again helpful for you in a sense, queuing based performance analysis helps answer fundamental design questions. What kind of questions we have? How many servers are needed to achieve the target response time? So these are something that to think in your mini project very specifically. At what load will the system saturate? Which component is the bottleneck under peak conditions? Right? So you can think these kinds of problems because you want to have a problem identification, a proper argument, set of data, and many facts to complete your mini project as well as the case study. You can't I don't think so within 2 to 3 hours you can complete. Even we have a lot of code completion things because you have to do it properly. Although these insights, performance engineers can design systems that are not only functional but also scalable, reliable, and cost effective. Some of the scenarios that we can think about, like computer systems and the CPUs, web servers, cloud servers, database systems, network systems, cloud resource allocations, and so on and so forth. So many aspects we have like computer systems, CPU models as MM1 or MG1 queues. So if we have multiple scenarios, then we can go for multiple situations. Used to estimate CPU utilization and response time under different workloads. This helps determine when to scale up hardware or introduce multi-threading. Then we can have MMC and we can have different kinds of database systems where the transactions arrival and query execution models as queuing networks and stuff. Here it helps to identify locking, delays, contention, and the query bottlenecks and so on and so forth. So we have cloud resource allocation, Poisson arrivals, Poisson, many facts we have at the end of the day. Here we have strengths and the limitations. Obviously, we have a lot of limitations. It provides the analytical solution for many system configurations and it's enabling predictive modeling before the actual deployment. So we can have we can run with very limited input parameters via lambda, mu, c kind of things. And if you have the limitations, it assumes stationary process where the arrival and service rates consistent over time. Real workloads may not follow exponential distributions, ignores correlations and presence in some traffic patterns. Analytical models may oversimplify the complexity. To handle these things, we have often combined giving analysis with simulation or the empirical data calibration for realistic predictions. So a lot of concepts we have to understand and run. So I have gone through in a bit of faster phase for you to discuss all these things. Before we wrap up, any questions you have? Do you have any questions to discuss?
No, sir.
All right. If you don't have any questions, thank you for attending today's session. I will share this details with you. So I know it's like very fast explanation going through. If it is the very first time that you are hearing all these things, it could be a bit complicated for some students. So if you haven't heard even these words, you have to go through all these things again. I will add some additional support for you in the LMS. Please go through all these things one by one and learn in like in a what do you call sophisticated path, so your life might be much easy, because I believe it could be a bit overwhelming for a very beginner to understand all these concepts in a one go. But for sure, you could be able to go through and understand these things. These are not very hard things, these are very easy. So you can learn actually. Don't worry. This is something very easy, but keep practicing and doing all these exercises, as well as do bit of mathematical work. Then for sure you can do the best in the examinations, as well as wherever that you are working. All right, I believe uh, I have covered up to session 1 to 6. Please go through, because the CAT will be in November, so I can go a bit more for this subject. So the CAT components, I was initially planned up to 1 to 6, if I'm not mistaken. So now I'm planning to continue from the entire unit 1. So completely unit 1 would be a question in the CAT examination, which is session 1 to 10. So you can learn from 1 to 10 to ready for the CAT examination. Planning to have only 4 questions, because it's 1 hour and 15 minutes. But it's not very hard, which would be very easy paper for you. So if you do it very well, it's a very easy paper for you. If you have done, math will be there for sure. There might be a question from both Poisson and exponential, as well as Kevin theory. So today's session might be worth for you. I believe it's valuable. All right, that's all for today and for this session. Thank you. See you. Bye bye. We'll meet soon.
Thank you, sir.